Okay, this is going to be a little bit of a weird smartboard lecture because over half of it is a PowerPoint. So um, I'm going to come over here and I'm going to start my PowerPoint and I'm going to go to slide 14, or sorry, 18. Okay, and so this next part of chapter 8 is about ionization energy. And ionization energy is interesting because ionization energy is the minimum energy required to remove an electron from a gaseous atom in its ground state. And interesting, ionization means how much energy it takes to remove the most loosely held electron because it's the minimum energy. And some books say the most loosely held electron. Other books say the minimum energy, which obviously the most loosely held electron is the easiest one to get away, so it is the minimum energy. And so this has to do with valence electrons. How much energy does it take to remove an electron from an atom to turn it into an ion, and actually a positive ion? And that's referred to as ionization energy, and it is measured in kilojoules per mole. So we actually remove 1 electron from 1 mole of atoms. Um, and it's in its gaseous, the electron is always being removed from the element in its gaseous state, and that's because if you have a solid like lithium and you zap it with energy, the first thing it's going to do is melt, and then after you zap it with more energy, the liquid vaporizes, and then if you zap it with more energy, that's when you can get the electrons to actually leave, the valence electrons leave. And so that's why it needs to be in the gaseous state. So if you look at this, I1 is referred to as the first ionization energy. It's on the reactant side because protons and electrons are attracted to each other. That's what Coulomb's law says. And in order to get one to leave, um, you have to add some energy to it. It won't just happen because the negative electron is attracted to the positive protons in the nucleus, and they're not just going to leave. You have to force them. It's an endothermic reaction. So I1 is the first ionization energy. I want you to notice this is a +1, this is a 1. The second ionization energy is how much energy it takes to remove the second electron. So the first electron's gone, then you rip away the second electron, and so notice I2, this is a +2, this is an I2. You're going to notice when I go to the sheet a couple slides down, it always takes more energy to remove the second electron than it does to the first electron. This is I3. Notice this is a 3 and this is a 3, and there's 1, 2, 3 electrons ripped away now. And then this part's very interesting. I3 is the biggest, I1 is the smallest, and I'm going to slide over a couple slides and then come back. The reason for that is when you take away 1 electron, now you have 1 more proton than electron. And so the nucleus is going to hold the valence electrons a little tighter when you try to remove the second one, because now the protons are winning by 1. And then when you try to remove the third one, that is hard to do also, because now it's harder because now you have 2 more protons than electrons. And so it holds them even um, more tightly. I really like this table. This is the second sheet in your purple packet, and this is why I like it. Hydrogen has 1 electron. It only has 1 ionization energy. Once you remove the first electron, you're done. It only has 1. There is no second, third, fourth, or fifth. Helium has 2 electrons, so there's a first ionization energy, a second ionization energy, and then they're gone. Lithium has 3, first, second, third. There is no fourth, fifth, and sixth. Boron has 5. There is no sixth. The rest of them, they only have the first 6. But what I was trying to show you on that slide before is it takes 1,086 kilojoules per mole to remove the first electron from each atom. But it takes 2,350, so more than twice as much energy to remove the second, because after you remove the first, there's more protons than electrons, and the protons hold the valence electrons more tightly, and so you really have to give it more energy to get them to leave. The third is even more. The fourth, look at this jump. This huge jump here we're going to talk about tomorrow. That's tomorrow's lecture. But here's, just look, this is the smallest, then this is bigger, this is bigger, this is bigger, this is bigger, this is bigger. So I wanted you to see that. I also like this. This is what you're going to graph. You're only going to go up to 20. Generally, the pattern I want you to see is the noble gases are the absolute hardest electrons to get hardest atoms to get an electron away from because they're incredibly stable. And the ones that are easiest to get the electrons away from are the alkali metals. If you look at period 2, this is period 2, lithium to neon. You'll notice that there's two blips: increase, decrease, increase, increase, decrease, increase, increase. From the start of the period to the end of the period, you can make the argument that it's getting the ionization energy is going up. Here's period 3. From the start of the period at sodium to the end of the period of argon, it's going up, and it does increase 6 of the 8 times. Increase, decrease, increase, increase, decrease, increase, increase. So the trend is that it's going up. If you look like at lithium, lithium is a little higher than sodium, is a little higher than potassium. So you'll see that as you move down a column, actually the ionization energy goes down because potassium is below lithium. Argon is below helium. And so that's part of what I want you to graph and notice. Okay, I'm going to draw this in, but here's the trends. I don't like to do it this way, but I'm going to do that. And again, we're only doing the trends for the A groups because if you go back and look at the slide here, things get, look where my arrow's pointing, things get dicey when the d orbitals come into play. I mean, up, 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 down, up, 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 down. There's really weird things happen when the d and f orbitals get involved, and so we are only going to do the A groups, the s and p orbitals. I'm going to do this. These are the two essays I'm going to help you write. Which of the following atoms has the larger first ionization energy, sodium or sulfur? Why? And which of the following atoms has the larger first ionization energy, fluorine or chlorine? And why? And we're going to come back to that. And that's actually all the slides I want to do today. Now, I'm really struggling with my tablet. I had to reinstall the drivers. I'm hoping it works. Otherwise, I'm just going to give up. So I'm going to grab my pen. I'm going to start with black. I'm going to try to draw the outline of the periodic table. And then I'm going to do a little bit of review. And it's really a bad picture, but you have no idea how much trouble I've been having tonight. It's better than I thought. Okay, now as you go across, this is review. As you go across from left to right, I told you on Monday that the radius increases. And the reason why the radius increases is because you go from left to right, you have increasing effective nuclear charge. I wrote increased. Let me see if I can grab this eraser. So I have increasing Zeph. So let me go through that again. So what happens is that as you go from left to right, the Zeph goes up. And when you have increasing nuclear charge, effective nuclear charge is in the numerator. And so when Zeph goes up, the Coulombic attraction becomes stronger. If the Coulombic attraction is stronger, the electrons are held more tightly, and if the electrons are held more tightly, the radius is smaller. So apparently Mrs. High is an idiot, and it doesn't increase, it decreases. And you can look at your sheet. I cannot believe I made that mistake. That as you go left to right across the row in a periodic table, the radius decreases. And the reason why it decreases is effective nuclear charge increases. That's in the numerator. If the numerator gets bigger, the force gets stronger. If the force gets stronger, it holds the valence electrons tighter. And if it holds the valence electrons tighter, the radius gets smaller. Now, but now I'm going to switch colors here. This is interesting. The radius increases, but the radius decreases, but the ionization energy increases. These are inversely proportional. So what happens is the radius gets smaller, but the ionization energy increases, but it's for the same reason. Hear me explain this. When you go from left to right, you have increasing Zeph, always. When you have increasing Zeph, you have stronger Coulombic attraction. When you have stronger Coulombic attraction, the valence electrons are held more tightly. Now here's the new thing. If they're held more tightly, it's harder to rip one away. And one of the things you got to know about energy is this idea that a high energy workout is difficult. Let's say you go to the gym and you're running, 6.5 miles an hour, or you're walking 2 miles an hour. We know that you burn more energy if you are working, if you are doing a difficult workout, it's high energy. And if you're doing an easy workout, it's low energy. And so the reason why the ionization energy increases is because the valence electrons are held more tightly, you have to use more energy to rip them away. So they're opposite. Now, coming up here, this guy up here, when you do radius, when the valence electrons are held more tightly, the radius shrinks. And then for ionization energy, when the valence electrons are held more tightly, you have to do a lot more work to get the electrons away. And remember, way back in chapter 6, we defined energy as the capacity to do work. So if the nucleus is holding the electrons very, very tightly, then you have to do a lot of work to get them away. And now this makes sense to me because, grabbing just a weird color over here, let's grab purple. This is helium. That's a noble gas. It's tiny. If you look at the graph, this is the absolute hardest atom to get electrons away from. Why? Because it's tiny, and because it has a lot of effective nuclear charge because it's way over here on the right. Now, grabbing this red pen, notice that atomic radius and ionization energy are always inversely proportional. So, okay, this is crazy. I have a really hard time with this. So let me try this again. When you go down, I will say that the radius increases. And we know that the reason the radius increases is that there's more shells and shielding electrons. And so let me just go through that again. There's more shells and more shielding electrons, which means the distance from the nucleus is bigger. When the distance from the nucleus is bigger, or there's more shells and shielding electrons, the Coulombic force is weaker. When the Coulombic force is weaker, the valence electrons aren't held as tightly, and because the valence electrons aren't held as tightly, the radius is bigger. Now, grabbing this green pen again, remember now these are opposites. Every time the radius increases, the ionization energy decreases. Again, let me explain why. If you have more shells and shielding electrons, I didn't mean to do that. Sorry, I hit the, come on. If you have more shells and shielding electrons, that means you have the distance from the nucleus is getting bigger. Distance is downstairs. When the number downstairs gets bigger, the Coulombic attraction gets weaker. If the Coulombic attraction is weaker, the valence electrons aren't held as tightly, and it doesn't take as much energy to rip an electron away because it's weak. And I made that analogy the other day of Purse snatchers don't target Clay Matthews. They target little old ladies because it's easier to get a purse away if there's a weak attraction than if there's a strong attraction type thing. Okay, so then, come on. What do I want to do now? Oh, so here are the essays. I rewrote them. So here's like the essay question. So which atom has a larger first ionization energy, um, sodium or sulfur? And then we need to justify our answer. Okay, so now what you need to know is that sodium and sulfur are in the same row. So sodium's in period 3 way over on the left. Sulfur is in period 3 over here on the right. And we know that if we go this way, Zeph increases. We also know that as you go this way, the radius decreases, but because the radius decreases, the ionization energy increases. So first of all, in the first sentence, I'm going to come down here. In the first sentence, you need to answer the question. You would say sulfur has the higher or the larger. Sulfur has the larger first ionization energy. Now, you know that, sorry, I'm jumping the gun. Okay, first sentence, answer the question. Sulfur is the larger first ionization energy. Then I got to go back up here and see how I worded it. Yeah, larger. You can say higher, greater, anything that means, anything that is a comparison word. All right, now, why? Well, what are you supposed to cite if you're in the same row? Zeph. So then you would say sulfur has a larger effective nuclear charge. You have to hit that first. Sulfur has a larger effective nuclear charge, so the Coulombic, eraser, this can be scary for me. All right, I did it. So the Coulombic attraction is stronger, period. And so then sulfur, better hit this extend page. Sulfur holds, I should say this, sorry. Here we go, eraser again, sorry. Sulfur's valence electrons are held more tightly. And I swear up to here, it's just like radius. So it takes more energy to remove a valence electron. And again, it should come full circle. More energy to remove a valence electron. Sulfur has a larger first ionization energy. So that's an example of one where they're in the same row or period. So now let's do another one. Let's add a new page. Come on, I can do this. Okay, so then here's the second one so that you see this. So here's our second one. Which atom has a smaller first ionization energy, fluorine or chlorine. Okay, now I'm being lazy. Justify. Okay, so first of all, here's your periodic table. Here's fluorine. Here's chlorine. They're in the same column. What are you supposed to cite for two elements in the same column? You're supposed to cite shells and shielding electrons. And so what we know is that as you go down, there's more shells and more shielding electrons. The radius gets bigger, but the ionization energy gets smaller because they're inversely proportional. And I want the smaller one, so the smaller one is the one furthest closest to the bottom. So then in the first sentence, I would say chlorine has a smaller first ionization energy. Answer the question. Which one's smaller? Chlorine. Now why? Chlorine has more shells and more shielding electrons. Okay, any linking words. So, therefore, hence, thus. Let's do thus. The Coulombic attraction is weaker. Why? Because in Coulomb's law, the distance from the nucleus to the edge of the cloud is in the denominator. If you divide by a bigger, more means bigger, number gets weaker. Chlorine's valence electrons are not held as tightly. So we need another linking word. So it takes less energy to remove a valence electron. Bingo. That's how you do these. That's how you do these. All right. Essay questions for ionization energy. All right, I just want to talk about one last thing. I want to talk about those blips, and this is what I'm going to do. I just used period 2 for an example. So here's period 2. Here are the elements in period 2. Lithium, and then beryllium, and then boron, carbon, nitrogen, oxygen, fluorine, neon. Now I went to the second page of your purple sheet, and here is the ionization energy. 520 kilojoules per mole, 899 kilojoules per mole, 801. I'm just getting these kilojoules per mole. This is 1086 kilojoules per mole. This is 1400 kilojoules per mole. This is 1314, I think, kilojoules per mole. This is 1680 kilojoules per mole, and this is 2080 kilojoules per mole. And you just look these up. I'm going to switch pen colors. Here's the deal. If I take, no, so this is the smallest, this is the largest, but look what happens. Bigger, smaller, bigger, bigger, smaller, bigger, bigger. Now, if we took this guy out and this guy out, look what happens. Bigger, 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 bigger. What I want you to understand is, why do beryllium and nitrogen screw up this trend? Because remember, it goes up, down, up, 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 down, up, up, up. What is going on here? Well, when I do the core notation, um, you will see what I want you to see. So here we go. Lithium, core notation is not neon, helium, 2s1. Beryllium is helium, 2s2. Boron is helium, 2s2, 2p1. Carbon is helium, 2s2, 2p2. Nitrogen is helium, 2s2, 2p3. Oxygen is helium, 2s2, 2p4. Fluorine is helium, 2s2, 2p5. And neon is helium, 2s2, 2p6, or if you prefer, this is also equal to neon. Now, a couple days ago, I did the stability triangle. Had it on the board. I'm going to do it again, and then I'm going to flip back up here. So, sorry, got to grab this. Okay, so here's the stability triangle. I drew this big triangle, and I said that the most stable electron configuration is noble gas core. Now, guys, when you have a really strong, stable electron configuration, it's very stable, it's very happy. In middle school, we call these happy atoms. And so what you'll notice is when you have a very stable core, it's very difficult to get an electron away from it because it's really stable. And so notice on that graph, noble gases are the absolute hardest atoms to get an electron away from. Okay, if it can't have a noble gas core, then its second choice is a full sublevel. And that means S2, D10, F14. Interesting. Let's go up here. Where do we have the first problem? Right here. Beryllium is especially stable because it has a full s orbital. Okay, now if it can't have a full sublevel, then it likes to have a half filled sublevel, which is S1, P3, D5, F7. And if it can't have that, it has no special arrangement, is the least stable. Or in this case, if it's not very stable, it's easy to get an electron away from it. Now look at this. What's causing the blips? I call them blips. What causes the blips in this trend? If I get rid of beryllium and nitrogen, that it would be increasing, 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 increasing. The blips are caused by the special stability of filled sublevels or half-filled sublevels. And if you go back to this PowerPoint, I'm not going to ding it up here, but, and we look at this graph right here, if I can find it, this one, you'll notice that we have some weird blips in here. This is because this is it goes S1, S2 is more, takes more energy because it's more stable than S2P1. You see it here and here. This one's very interesting because this is D10. Atomic number 30 is zinc. Zinc ends in D10, and D10 is very stable. If you look at the stability triangle, you know, D10 is a full sublevel. So if you look here, going back to this PowerPoint, not all these other ones, you'll see, I don't know what I did with that. So you'll see that the noble gases, which is the most stable arrangement, they're at the top. The blips are caused by S2, P3, D10. Otherwise, if you take out the blips, we have pretty perfect trends. So all I want to tell you about this is really all you need to know for the AP exam, is that the blips in the trends for ionization energy are a direct result of the special stability of filled sublevels or half-filled sublevels. That's what causes the blips. All right, that is it for now. Do your graph. Do your graph and do your book assignment and give it your best shot. You can ask me